So let's apply compound interest here. Let me get it to fit. Yeah, here we go. So how long would it take for $10,000 to triple if our annual interest, APR, annual percentage rate, was 6% and we compounded that quarterly? All right, so um, if you watch some of my other videos on how to derive, how to derive the compound interest formula, I've got several videos on this, but the formula for compound interest is something like this. The amount we want in the end is equal to the principal, P, the initial investment, times 1 plus your rate of growth, annual rate of growth, divided by your compounds, all to the compounds times the number of years that we're going to do it. So we're just going to start plugging in all of this. So hopefully somewhere you found this formula, but again, just to recap, this stands for your initial investment. C stands for your compounds. R stands for your rate of growth. Again, C is compounds, and T is time in years. And then A is going to stand for your final amount, what we want to end up with. Well, you have to ask yourself, what do we want to end up with? Well, we want to end up with it tripling. So we want to end up with $30,000. And we started with $10,000. And it was 1 plus, our rate of growth was 6%, divided by 4, because we compounded it quarterly, and then 4 for that compound, but our t is time, and we don't know that. That is what we're trying to solve. So what we're going to have to do is, we could guess and check. You could start plugging numbers in there for t, and honestly, with guess and check, you could probably hit the number pretty fast, but it's going to be around 8%. Oh, maybe. No, 18 years, sorry. Wrong problem. Wrong thinking. So 18 years is you got to think about that. I don't know where 8% came from. My brain's not working. Oh, it's the next problem. But anyway, so we got to isolate the t. Well, whenever you have an exponent, that's why we have logarithms, to help us do that without guess and check. We could guess and check. It's a beautiful thing. Don't ever forget about it. Or don't ever throw it away, because sometimes you'll forget all these fancy tricks and these fancy high-power problem-solving tools that we have, like the logarithm. So to use a logarithm on this, the first thing you have to do is isolate this exponential term, the base and the exponent. So I'm going to divide by 10,000 to get that out of there, since it's multiplied. So I'm going to invert it, inverse divide by 10,000 in both cases. And so we'd have 3 equals, well, 1 plus 0.06 divided by 4 is 1.015, all to the 4t. Okay, now that that exponent's isolated, we can go ahead and apply a logarithm to that. Now, you could use common log or natural log, whatever you prefer. I prefer the natural log. So I'm going to put in here, sorry, I'm going to squeeze it in, so I had to move the equal sign. So natural log of 3 equals the natural log of 1.015 to the 4t. Now, if you look at some of my other videos, I always mention the third rule. And the third rule for me with logarithms is, if you have a logarithm to an exponential power, the whole reason we use the log on both sides is so that that pops to the front. And so this could be rewritten as natural log of 3 equals 4 times t times the natural log of 1.015. Okay? So at this point, it is simply a matter of dividing to solve this thing. So to solve this thing, we want to get t by itself. So we'd need to divide by 4 and by ln, natural log of 1.015. So divided by 4, natural log 1.015. So your time t is your natural log of 3 divided by 4 natural log of 1.015. And so plug that baby in to whatever calculator you have, and you know you got it right when you hit this as an answer, as an approximate answer. So I'll put the squigglies here. So it's going to take about 18.45 years to triple our investment at 6% interest compounded quarterly. So kind of a long time, but doable. And so that's that problem. And just make sure, make sure you can plug that into your calculator correctly. That's kind of a trick depending on the calculator you have. And so I'll leave that up to you to learn how to use your calculator. Next problem, and let's see, hopefully it'll fit. Oh, dang. So let me make it smaller so it does fit. There we go. Move it around here. And so let's say, this is kind of a fun problem. Let's say we start our lives with $10,000. So our mom and dad threw $10,000 in our bank account the second we were born. Knowing we want to be a millionaire by the age of 55, what interest rate would we have to have using interest that compounds continuously? So what's the investment amount we need to become a millionaire if we start when we are just born, and we're going to hopefully be there by the time we're 55 so we can enjoy that $1 million? Well, first off, you need to know the formula for compounding continuously. And I have several videos on how to get to this, but y equals p e to the rt. I call it PERT, and maybe many other people do too. But PERT, just to kind of decipher everything, and I hate that I use y, let's kind of keep it consistent with the last problem. A is our final amount we want to end up with. P is principal. Okay, E stands for the Euler number. It's the inverse of the natural log. And so you want to, if you don't know what the Euler number is, go look that up. But we know e to the first is approximately 2.71 blah, 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 something, something, something. Or we know the definition of e is a limit as n approaches infinity of 1 plus 1 over n to the nth power. So if you throw in really large numbers for n, you end up with that 2.71 blah, 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 blah. I think I have that right. I'll have to look it up. But anyway, e is like pi. It's an irrational number that we're going to use here. R, and again, if you want to know more about it, please look it up. Look up Euler number. Lots and lots of videos about it and what we do with it. R is your rate of growth, and T is your time. So let's plug in what we have. Well, we know our time is going to be 55 years. We know our principal we're going to start out with is $10,000, and we're going to end up with $1 million. And so we got everything but our rate. R is what we're trying to solve. So let's go ahead and plug that in and solve it. So, 1 million equals, we start out with 10,000 for P, e to the rate of growth, which we don't know, times T, which is 55 years. So 55R if you wanted to rearrange that. And so again, we could use guess and check, but let's use these powerful math tools that we have. So we want to, anytime you have an exponent, a variable in the exponent that we have to solve for, we're going to have to use a logarithm. And so let's use the natural logarithm, since this is the Euler number and they're inverses to each other. So first off, isolate the exponent. So we're going to divide by 10,000 on both sides. I'll put the commas in there. And 1 million divided by 10,000, you start crossing out zeros, is 100. So we've got this formula, 100 equals e to the 55r. because that bothers me to have R55. And so your next step is to natural log both sides of that. So we're going to natural log here, kind of like dividing both sides, doing the inverse of both sides. Wherever you do to the left, you can do to the right. And the reason, again, we do that is because when you log with an exponent, that exponent pops out front, rule 3. So natural log of 100 equals 55R natural log of E. Again, natural log E cancel out, and you just have natural log E cancel out. So you have 55 times your rate of growth is equal to the natural log of 100. So now you can get your calculator out, find out what natural log of 100 is, and divide that by 55, because we're solving for R. So your rate of growth is natural log 100 divided by 55. And when you do that, when you take natural log of 100 divided by 55, you get a rate of growth of 0.084, approximately. I'm rounding, of course. And so if you invest $10,000 and you get 8.4% interest compounded continuously, you will end up with $1 million when you turn 55. So we need to invest it in 8.4%. Well, that's a pretty hefty investment. That'd be nice I wish my portfolio was gaining at 8.4%, but it is not right now. So there's a couple of application problems that I think are kind of fun. Best of luck with these, and I will see you next time.